A stacked GRU RNN based approach for predicting the wind energy and electricity load. My teammates are M. Vaishnavi, Nanduri Vinay, and myself, Shweta. Abstract of the project. The experimental result shows a process method achieving an accurate energy predicting for effective smart grid operation. Keywords used in abstract: electricity load, forecasting data, GRU RNN, renewable energy, and SVM. The list of abbreviations. Introduction. With the integrated of the latest information communication technology, the traditional grid is transforming a rapid into a smart grid. Smart grid is aiming to provide the consumers with renewable, reliable, economical, sustainable, secure, and effective, providing the energy supply by monitoring, protecting, optimizing the production, and distributing and consuming the electric energy. The predicting both energy production and electricity load play a vital role in balancing and secure grid scheduling and operation. Further investigation is reduced to model parameter and improving the training efficiency is needed to develop accurate and efficient method for predicting a renewable energy generation and electricity load with increasing uncertainties from both supply and demands. Aim of the project. The project purpose of a novel predicting method for renewable energy production and electricity load based on improved stacked GRU RNN with a reduced model parameter and new training mechanism. Project domain. The processor method can deal with both multiple variant and univariant cases. The effectiveness of the method is demonstrated by conducting 2 experiments, including a multiple variant wind energy prediction and univariant electricity load prediction. Scope of the project. A system is essential to build which will work with the maximum accuracy and should consider all improvement factors that could be influences the result of prediction. Literature review. We have taken a literature review from the net. The topics are wind power forecasting with deep learning networks, and 2, a review of deep learning for renewable energy forecasting, 3, a hybrid deep learning based on neural network for 24 hours ahead with wind power forecasting, 4, a short-term electric load and price forecasting using the enhanced extreme learning machine or optimization in smart grid, and 5, intermitting the stochastic characters of renewable energy sources, consequence, cost of intermittence, and brief of forecasting. 6, a long-term load forecasting model based on mass ANN and LR methods. 7, short and medium term forecasting of cooling and heating load demands in a building environment with data mining based approach. 8, solar power predicting based on satellite image and support vector mechanism. 9, hourly solar irradiance predicting based on support vector machine and its error analysis. 10, deep neural network based on demand side short term loading forecast. Project description. Existing system. Our existing system design a novel solar predicting scheme for 1 hour ahead prediction of a solar irradiance based on various methodology factors included the cloud cover and SVM. A K-mean cluster algorithms applied to cover a methodological data and the entire data classified into 3 clusters based on similar daily weather type. Disadvantage: high error prediction accuracy parameter. It requires more time to predict the energies. Proposed system. Our proposed system proposes a novel prediction method for renewable energy production and electricity load based on the improved stack GRU RNN with reduced model parameter and new training mechanism. Advantages: it can perform a accurate energy prediction using time series data with monitoring parameter. It saves the computational cost and requires less training data. Feasibility study. Feasibility study for predicting electricity load and wind energy using a machine learning could involve analysis the current state of wind power data collections and predicting methodology. Economical feasibility. Economical feasibility of implementing electricity load and wind energy prediction system using a machine learning algorithm could depend on the cost of the technology and potential financial benefits. Technical feasibility. Technical feasibility of implementing electricity load and wind energy prediction system using machine learning algorithm involves accessing the capacity of hardware and software system to manage a large amount of data. Social feasibility. Social feasibility is implementing electricity load wind energy prediction system using the machine learning algorithm to involve analyzing the potential social impact of communities and stakeholders. System specifications. System specifications is of a Google Colab will need a minimum CPU equivalent to an internal core i3. And we move to methodologies.
The architecture of our proposed system is depicted in figure 4.1. This shows the detailed and abstract view of the system. By collecting the dataset of load data and weather data from NYISO, after monitoring the various parameters at different time and weather, and pre-processing the data by removing the irrelevant values and null values from the dataset, and applying stacked GRU RNN approach to predict the accuracy of wind energy and electricity load. Data flow diagram of our proposed methodology is depicted in figure 4.2. It applies the stacked GRU RNN approach by collecting the load data and weather data to pre-process the data by removing irrelevant data set. The prediction accuracy will be analyzed by RMSE and MAE values. The use case diagram for the proposed methodology is depicted in figure 4.3. It shows the process of user collecting the dataset and pre-processing the data by removing the irrelevant data, applying GRU RNN based approach to split the training and testing dataset, evaluating the accuracy by analyzing the error values. Class diagram. The class contains data collection with dataset as load data and weather data. By uploading the inputs of the dataset in the GRU RNN approach, it will split the dataset into training and testing data. After that, evaluating the RMSE and ME values to predict the accuracy of electricity load. Sequence diagram. Sequence diagram for the proposed methodology is depicted in figure 4.5. The collected dataset such as load data and weather data will be pre-processing it by removing irrelevant values and null values. The stacked GRU RNN will split its data into training and testing data. The evaluated accuracy will be analyzed with RMSE and ME values so that the predicted value is accurate. Collaboration diagram. The collected dataset contains the load dataset and weather dataset. The data will pre-process it. Applying stacked GRU RNN based approach, the data will be in split in training dataset and testing dataset. The evaluated value will be analyzed by RMSE and ME values. Activity diagram for the proposed methodology. By collecting the data sets such as load data and weather data, the data will pre-process it, applying the stacked GR RNN based approach to split the training data and testing data, evaluating the RMSE and MAE values from the actual data to predict the accuracy of the electricity load and weather data. Algorithm. A new framework for both prediction of renewable energy and electricity load is proposed by using improved stacked GR RNN based approach. The developed approach can perform accurate energy prediction using time series data with monitoring parameters. The electricity load based on a improved stacked GR RNN with reduced model parameters. Model description. Data set collection. The collected data from the two primary sources, NYISO load data and weather data. The load data we obtain from NYISO, which measures the electric power load usage every 5 minutes, was no exception. For every 1 hour, the data was resampled so that each data set would match according to it. The weather data contains data point for 11 monitoring variable every day. The stacked GRNN model with proposed GRU structure and the improved training algorithm. Train the model with training samples to establish an accurate mapping between selected monitoring parameters. To determine the input variable for prediction task and correlation analysis is performed. Prediction. To verify the prediction performance of the stacked GRNN model using testing sample to evaluate model performance, we optimize for more precise short-term forecasting consistency in forecasting. There, two indices are selected to quantitatively and comprehensively evaluate the prediction performance, RMSE and MAE. Steps to implement the project. Collection of dataset, applying stacked GRU RNN based approach, and evaluating and predicting.
Now I'm going to explain about implementation and testing of a project, input and output. Here we can see that we have collected different types of data sets and that are arranged in an order in the form of a tabular. The weather data set input diagram from the proposed methodology is depicted in figure 5.1. This includes the temperature, humidity, perception levels, air pressure, wind speed, and direction, etc. Here we can see that there are timings of sunrise and sunset and moonrise and moonset and different weather climatic conditions that have been noted down. And we can see the wind direction and speed collected over a specific period of time. And now we're going to execute the values that are given in the form of encoding. And in the figure 5.2, we can see the lines that have been drawn. The blue color line represents the prediction data, and the red color lines predicts an actual data. Here we're going to perform different types of testing. They are unit testing, system testing, and integration testing. Unit testing. The tests are based upon the deep learning method of the stacked GR RNN models, whether it is properly initialized and configured with the proper hyperparameters and layers. The system can directly classify the difference between the actual data and predicted data types in different types, such as heavy climate, normal climate, or climatic changes that are going to be taken. And we got the result. The test of the unit testing is validated the accuracy of prediction values that can be measured using statistical techniques such as MAE and RMSE. Next, integration testing. Test the system that can properly receive and process real-time weather data values from multiple areas in different seasons. And we are going to test a system that can effectively identify the changes in the climate scenarios, whether there may be high changes in climate conditions that may lead to any obstacles. And the result of integration testing. This test involves simulating different scenarios and evaluating the behavior of the prediction model into the larger system and to ensure that it is functioning as intended. The test result and proposed methodology in integration testing is successfully passed the test. And the next one is system testing. Here we are having different types. We are going to prepare the data and we are going to train the model and we are performing system integration testing. The data preparation set of weather reports is collected from previous years that is going to be compared with the present year data reports for testing. The data set to cover a range of different climatic changes in the same area, which is helpful for the testing purpose. The model is trained on deep learning method on the prepared data set of the weather report values that are used to improve the accuracy of predicting values and generating the electricity load that has been consumed by the customer. System testing. Here the input we are going to do in three different kinds. That is, we are going to prepare the data and we are going to train the data. Then we are going to use it for system integration. The data set preparation of weather reports is collected from previous years that is going to be compared with the present year data reports for testing. The model is trained on the deep learning method on the prepared data set of weather reports and values that are used to improve the accuracy of predicting values and generating the electricity load that has been consumed by the customers. And system integration. The algorithm is integrated with other technologies such as RNN and GRU systems that are used to improve the accuracy and efficiency of the weather reports. And the result of system testing. The system is to identify any issues with the integration of the prediction model in the system and whether it is going to ensure that the overall wind energy and electricity load is operating efficiently and effectively. And next one is the test result. Here we can see the graph that is displayed in two different colors. The blue color line that shows us prediction data and the red color line shows the actual data. By observing the figure 5.3, we can see the output of electricity load and wind energy. The diagram depicts the proposed methodology and it predicts the values that can be obtained by feeding the trained model with the data set and using it to make prediction for wind energy. The accuracy of prediction can be determined by comparing it to an actual data through various techniques such as RMSE and MAE. And next one is results and discussions. Efficiency of a proposed system. The effectiveness of a proposed approach for both prediction and renewable energy and electricity load. We are going to perform two experiments are wind energy prediction using multiple weather parameters and electricity load using low data. We are going to improve the stacked GRU RNN reduced to the model complexity by using few parameters which save the computation cost and requires less training data. We can perform accurate energy prediction using time series data with monitoring parameters. In figure 6.2, comparison, we are going to compare of existing and proposed system. Here we can see the results that are shown in the pictures. And the existing system, SVM. The existing method is based on SVM is proposed to predict the wind energy as depicted as figure 6.1. The inputs of the prediction method are simply weather predictions and electricity loads in every 15 days. In general, the more previous loads as inputs, the better training performance could be. The SVM result of prediction of wind energy and perform compared to stacked GRU RNN approach in accuracy of the prediction. However, when the number of previous loads is too much, the problem of overfitting arises. And the proposed system, stacked GRU RNN based approach. The proposed method of stacked GRU RNN based approach is a model type of artificial neural network. It is known as ANN that employs gating mechanisms to control the flow of information and it is allowing to capture long-term dependencies in temporal data. The stacked GRU RNN based approach result for prediction of wind energy is depicted in figure 6.1. The stacked GRU RNN based approach outperforms SVM in accuracy of the prediction. It is used to predict wind energy at a specific site. And the parameters such as air density, temperature, humidity, and wind speed have been utilized. Thus, it can be seen that the stacked GRU RNN based approach is a superior choice for wind prediction compared to SVM. In 6.3, the sample code is displayed. This is the sample code that we are going to use in a project, and this is the input that we are going to initialize into a project, and this is the output that we got from the given output. And next, my friend will continue.
Now we are seeing our source code of project. We are giving the data set and we are compiling it, and we will get the output in a graphic form by predicting the actual data. we are comparing between the prediction and the actual data, and we are getting the graphic. We are getting into a graphical form. Blue is in a prediction, and red is an actual data. And we are looking a prediction of electricity load.
Conclusion and future enhancement. Conclusion. To achieve accurate prediction of energy and electricity load for effective smart grid management, a novel method based on improved stack GRU RNN and multiple monitoring parameters was presented in this work. The improved GRU RNN reduced the model complexity by using fewer parameters, which save the computational cost and requires less training data. Possible experimental result on real wind energy generation and electricity load prediction demonstrated the feasibility and superiority of the proposed approach by comparing it with other state-of-art data-driven prediction methods. Future enhancement. However, there are still exists some limitation in this method. The hyperparameters are determined by experience. The training time is much longer than shallow models, and training samples of considerable length are indeed. Possible future work includes how to improve the prediction performance by further improving the training strategy and investigating additional monitoring parameters, and to precisely model and accurately predict the energy generation from multiple renewable energy sources, and how to detect anomalies in electricity load caused by extreme cases. This is our plagiarism report. This is our source code. This is our poster presentation. And these are some references we have took from the internet. Thank you.